Good morning. This is the first segment of section 7.2, and I want to apologize. Well, you may not notice it, but I recorded this lecture previously, and then when I on playback and review, I realized that the video was fine, but that the audio was all kinds of garbled and messed up. So I'm going to be repeating this lecture. But that means that I've already kind of produced the material, so I won't be writing it. I'll actually just be referring to it as we go on. So here's the sort of setup. But previously in 7.1, we talked about situations where we either have angle, side angle, or angle, angle, side. And in section 7.2, we're going to look at so-called side-side angle. Now, remember, side-side angle is not a congruence argument, but there are certain criterion whereby it could be. Usually we end up with situations where either there's no solutions, possibly only one solution, and then there are also situations where we can actually have two solutions. So whenever you're confronted by a triangle that starts off with a side-side angle, you have to go through a series of processes to determine whether or not it is possible. If it only has one solution, in which case it's relatively easy to work with, or does it have two solutions? And if it does have two solutions, in most cases, and this is where the biggest problem comes in with like homework in this section, is that you, generally speaking, have to do both solutions. You have to solve both solutions. Now, in a test situation, perhaps I might tell you which, generally speaking, because this is a new task, using the law of sines actually is pretty trivial. I find that students don't really have too much trouble using that equation. Where the problem comes in is when you start taking an inverse trig function. And that is really why we spent so much time in the previous sections talking about inverse trig functions and how to find multiple solutions and that sort of thing. So without further ado, first off, let me step over here to the document camera. Now you're going to see this little piece of paper in a way because I'm kind of blocking what I was about to write. So section 7.2, page 1. Now, here's the thing. It depends on whether the very first criterion is that you're going to be given one angle and two sides. You want to be able to make sure that this is in fact side-side angle and not side angle side, because if it's side angle side, then it's solved an entirely different way and is it's relatively straightforward. Side-side angle is the one that gives people the most headache. So if you have a situation where you have side-side angle, so this would be where you have one angle, its opposite side, and another side. Okay, it's very deceptive because then you're like, oh, well, I can use opposite sides and pair it up, and I can use the law of sines, which is true. That is the method that we're going to use to solve this. But you have to first decide because you'll eventually use an inverse trig function to solve it, and either one of the possible solutions is correct. You have to establish whether things work or not. So here's a setup. The first thing that one might consider is if the given angle is obtuse. So in this situation, I'm given a value of some obtuse angle for B. Here's my knowns. B is some obtuse angle, and A is some known distance. Now, if B, which is kind of what I'm trying to represent here, if B is too short, it's not possible for B to get down to this terminal ray on angle B, right? It just cannot make it, right? It'll be sort of swinging freely here. And if that's the case, then there is no solution. So for obtuse triangles, you either have no solution or you have one solution where that opposite side is somehow long enough to get there. So what's the criterion? Well, the minimum distance is that it has to be a little bit longer than A. If it was just even a little bit longer, you'd have a triangle. If it's equal, then it's not a triangle at all. It's just a line segment, which is a very uninteresting problem. But as I said, so the first thing you're asking yourself when you have side-side angle is is the angle given acute or obtuse? If it's a right angle, well, that makes it a much easier problem. But anyway, so be it. So if you have an obtuse angle, there's two criteria. If angle B is obtuse and A is greater than or equal to B, then there's no solution. So this is the situation where B is kind of shorter. I mean, it could be equal, but again, that just is a line segment. So your first criterion, if you can establish that that angle B is obtuse, or whatever the angle is you're given, and that the opposite side is actually shorter than the other side, then you're done. There is no solution. There's no triangle that this happens for. On the other hand, if B is even slightly larger than A, there will be exactly one solution, and it will always have a solution. There isn't a sort of a weird sort of secondary criterion where that happens. And if it does have a solution, then you use the law of signs with impunity. You don't have to worry about the so-called ambiguous case because it's not ambiguous. There's exactly one solution, and angle A will be acute. Okay, so you have an obtuse angle, acute, and then you follow up by finding a third angle, etc. We'll cover these methods in another segment where we actually do some of these. So don't get too overwhelmed by the sort of preamble here. Okay, so what if the angle is actually acute? What if the angle that's given is acute? So I got a lot of drawing here because as I did this in the first video, I kind of drew piece after piece after piece and got a little busy. So I just want you to think about angle B is an acute angle. Angle A, or distance A, is some number, and B is somehow less than A. You have, but it has to be really short, right? So if B is very, very small, then there's no way for it to reach the terminal ray of angle B, and so you'd have no triangle. Now, what's the criterion here? Well, if for some reason, if B is less than the altitude of the proposed triangle, then that's where you're going to start to have problems. If it's too short to even reach on a perpendicular intersection, then you simply can't have a triangle. Now, recall from our discussion about finding areas of triangles and some other sorts of situations, we said that the altitude of a triangle is going to be, you can solve a sine of B is h over A, so h is equal to a sine B. And so if B is somehow less than this altitude, then it will never reach the terminal ray, and so you have no solution. Now, for some reason, if B is actually equal to the altitude, it turns out that there is one and only one triangle that will do that, so you have a single solution, and it will actually be a right triangle, which makes it much easier to solve. That's a very unlikely scenario to happen. And so, but it is one of the possibilities. Now, if for some reason B is a little bit bigger than the altitude, but not bigger than A, right? Then you end up with possibility of two solutions. One, which is where angle A is, I didn't even label this, sorry, angle A is acute, right? And or another solution where angle A is obtuse. This is the ambiguous case, and this is what this whole section is about. And it leads into this idea of inverse sines and that sort of thing. So this is kind of the critical part here. When you have when the value of B is between the altitude and value of A, and I'm just using those labels, but this is where you end up with a situation where you have two triangles, one of which has an acute angle, is the first angle you're going to solve for, or it has an obtuse angle. Now, I want you to also note that there's a relationship between those two possible values. Maybe I'll just call this A prime or something. Note that since this triangle that's formed is an isosceles triangle, and if we forget the actual triangle we're trying to solve, then these base angles are congruent. Right? So this angle is equal, the measure of this angle is equal to the measure of this angle. But that means that this angle, which is the supplement of this interior angle is also the supplement of this angle. So we have, real quickly, we have a way to actually find both of these angles. So in this scenario where you have the ambiguous case of law of sines, what happens is you will solve using the law of sines and you end up with this angle. The other solution is just the supplement. And that's kind of the key to being able to do this. Now, as B becomes a larger value, at some point when it's actually equal to A, again, you're back to a situation where you have a line segment, but there's also a possibility of an alternative solution out here, right? So there is maybe, which I didn't draw the first time, maybe this sort of third situation where B is actually too big to get a double to get the two solutions in here, but maybe is now back out on this ray some other place. So at the instant that B, if we think about B increasing, as B gets to A, that is not a triangle, but there is one over here. It would be an isosceles triangle. And as B gets larger, larger and larger, you do end up with other triangles as well. So the criterion then, if we break it down, if B is acute and B is less than the altitude of the proposed triangle, then there's no solution. There's no way to create a triangle. And what ends up happening is if you didn't recognize that and you start calculating, you end up with an error. If, on the other hand, B is equal to the altitude, then this is a right triangle. And angle A is 90 degrees, exactly 90 degrees. Now that's, like I said, that just does not happen in a measured situation. You just never have a perfectly right triangle, but maybe it could happen theoretically. And then if B is between the value, a little bit bigger than the altitude, but not as big as side A, this is where you have two solutions. And when you have these two solutions, this is what is called the ambiguous case. And it's the ambiguous case of the law of sines. You do actually use the law of sines to solve this problem, but you have to recognize that there are two possible solutions. Okay, and then finally, if B is greater than A, greater than or equal to, then there is exactly one solution and angle A is acute. Right, and that is the basic criterion for these. This is the more complicated thing to remember, but I would say that in trying to absorb this information, it's not about memorizing these flowcharts, right? It's about saying what does it geometrically look like? These two pictures are powerful because it's like here, you're really just separating them up into obtuse or acute. Here it's obtuse. You really can, depending on the relationship between A and B, you can decide without reference to this flowchart whether or not this has a solution. This one is a little bit more tricky, but you have to think about these three different scenarios. A is a little too short. Maybe B is a little too short. Maybe B is exactly the right length. Maybe B is a little bit bigger, or maybe B is even larger than that. And so this one tends to be the one that drives people crazy. Now, I will say that it has been my experience that with students working on these problems in the homework or wherever else, tests, everything, it is really, really common to forget that there are actually two possible solutions. And it's because I think it really has to do with a lack of familiarity with the process. So what I would suggest in order to be able to nail this down is to do as many of these particular problems as possible. And I've assigned some problems at the, there's like some conceptual problems in the homework that actually ask you to figure out, why is there only one solution, or why are there multiple solutions, whatever else. Those why questions are much harder to answer than how or what. And I'm hoping that you'll take those exercises seriously to really sort of work with this flow chart to decide in what situation is whatever going on. And this is the arguments to use, right? So that will come up in the homework. It's not a huge amount of points, but I have rewritten the problem statement for that problem so that it's clear what I'm actually asking for. Because in the problem statement, the one I'm thinking of is, I think maybe the first one in this section, it asks you to just simply state how many solutions are there. And I've expanded the problem to say something to the effect of, why is there a certain number of solutions? And so you can take a look at that. But really, this is more about critical thinking than really just following some recipe. So anyways, well, I don't want to get too verbose on this. We're going to end up, since I've already actually recorded the second segment for this section, I will tell you that we're going to end up with 3. The second one is relatively short. This one is probably also relatively short. I'm not quite sure on my time yet. And then the third, so in the next segment, we're going to solve this case where we have obtuse, and we're going to look at both of these situations. And then in the third segment, which I haven't recorded yet, we'll focus on the situation where B is acute. So I will see you again in the next segment.